Hello everyone, in this video I'm going to be talking about how to convert alcohols to alkyl halides. Alcohols have a bad leaving group, so you really can't directly convert alcohols to alkyl halide. Before you do so, you would have to convert the OH or the alcohol group into a good leaving group, and there are numerous ways you can actually convert the OH into a good leaving group, and some of the examples being using tousled chloride, Mesyl chloride, or using a binary acid, PCl3, PBr3, and SOCl2. So I'm going to go over those one by one, and I'm going to try to be as brief as I could in those cases. Let's start with using either tousled chloride or Mesyl chloride. So tousled chloride is actually a para-toluene sulfonyl chloride, and this is actually the structure I have drawn on the right side. You don't really necessarily have to know the structure. A lot of time, what they're going to be doing would be writing the tousled chloride as TsCl, and they're going to be writing the Mesyl chloride, which is actually methane sulfonyl chloride, as MsCl. And then in addition to that, you would be needing a not nucleophilic base, which is going to be the pyridine in this particular case. So suppose if I take an example of using a TsCl or tousled chloride here, so this secondary alcohol with the reaction of tousled chloride, and I'm going to be using the pyridine as my non-nucleophilic base there, we will end up making a good leaving group. So I'm just going to copy this down. So I'll take this part out, and we're going to have an OTS here. So all of a sudden, this is a good leaving group. The other thing you want to be aware here is you didn't really change the stereochemistry of that chiral carbon. And this usually works well whenever you have a primary and a secondary alcohols. The tertiary alcohol is a little bit crowded, so it's not going to work that well. Now, in terms of mechanistically, what really happened, let's look at that. The mechanism is actually fairly straightforward. So if I just copy this part down here, just going to bring that down here, maybe make it a little bit smaller here. I know there is a 2 lone pairs of electrons on the oxygen, so we got this sulfur as your electrophile there. So we're going to have this nucleophile on the oxygen attacking this sulfur, and we're going to be breaking up this pi bond between the oxygen and the sulfur here. So in the process, this is what it's going to be made. So I'm just going to go ahead and copy this down right here. And then remember, you're still going to have, this is a new bond. I'm going to draw out this oxygen here, and we still have one double bond with the other oxygen. We got the chloride here, and then we got this group right there. And obviously this oxygen that was on the alcohol still going to have the hydrogen there, so don't forget that. So I'm going to go ahead and actually change the color there so that you can see the better. And this oxygen is going to get a positive charge. Now, all of a sudden, when you do this, the next step, this electron pair that's on the oxygen is going to come back, and when it comes back, it's going to knock out this chloride, which is your leaving group there. All right, so let me just copy this down here, and I'm going to take out part of it. Now you got a double bond there, and obviously you're going to have a Cl minus that has left the solution. Now this is still a positive charge on that oxygen, so what we need to do in the next step would be using the pyridine now to deprotonate that particular proton there. So I'm going to go ahead and use this pyridine, a nitrogen lone pair is going to be used to grab that proton, and this is going to go back on the oxygen here, and that's what it's going to make at the end of the day. Now, instead of drawing all this thing, what we really do, we usually write this in the form of an OTS. So that's why either you're going to see this being written as an OTS, or if you're using an Mesyl chloride, you're going to be seeing this as written OMS. And keep in mind you don't really change the stereochemistry. Now, once you have this OTS installed there, this is a really good leaving group, and it behaves like alkyl halides at this point, and you can do a bunch of reactions to it. Now, this particular structure I have drawn is in a secondary, and you can install the tosylate groups on the primary alcohols as well. But if you have a primary alcohol, you're not going to have to worry about the stereochemistry, because for the most part, the primary alcohols are not going to be chiral except you have a deuterium there. But here you have this, once you have this OTS installed there, I can have this electrophilic carbon, which is going to be bearing a partial positive charge, and oxygen is going to be partial negative. So I can have a bunch of nucleophile attacking this particular carbon from the backside. And when it attacks from the backside, it's going to have an inversion in the stereochemistry. So suppose in the first case, what's happening here, I got a H minus as my source of nucleophile from the LiLH4, and when it does the backside attack, it's gonna have an inversion in the stereochemistry. This is how it's gonna look like. Now, I don't really have to draw this going back into the page because it's really not chiral, but I'm just showing you how it's gonna be appearing if this nucleophile was not the hydrogen. So if this is not a chiral, you don't really have to draw this in and out of the page. But suppose I'm using something like NaX. X could be either bromine, iodine, and chloride. So I'm going back to the alkyl halides now, and then I'm just gonna copy this down here, and instead of having the hydrogen, I'm gonna have the X here. So X could be either chlorine, bromine, or iodine. So I clearly have an inversion in the stereochemistry in this particular case. You could also very well have the cyanide as your nucleophile here. So cyanide could be, you could be using either NaCN or KCN. Then you would have the CN attached to that particular carbon going back into the page. You can also have the NaSH, where SH minus would have been your nucleophile, and that would be going back into the page when it's attached to that carbon. Now, these are not only limited to the substitution reaction, so all these guys are SN2, where you have an inversion of configuration, but you can also do E2 reaction if you're using a strong base. So I can use NaH, and if you're using an NaH, which is a small non-nucleophilic strong base, it's going to do an E2 reaction, and it's going to do with respect to Zaitsev rule. So I'm going to be making a most substituted product. So you're not only doing the substitution reactions, but you can also do the elimination reaction. The other reaction I want to talk about here, since we're talking about the elimination as well, what if I use a bulky base, something like an aldehyde or tart butoxide or DBU? Any of those bulky bases will still be an E2 mechanism, but now we're going to be doing a Hofmann product here, because the aldehyde being in a bulky base is going to remove the most readily available proton, and it's going to make the least substituted alkene. So if you have forgotten your Zaitsev and Hofmann rules, you want to go back and learn E1 and E2 and their criteria. So this is how you're going to be using the TsCl and MsCl in order to convert those back to an alkyl halides. And in addition to, you can also do elimination reactions. Now, let's talk about how you can actually use a binary acid to do the same thing. The difference here is obviously going to be you doing all these reactions in acidic conditions. I can use HI, HBr, and HCl. Obviously, HBr and HCl are going to be the most common one. The HI is also seen here and there. Now, if I want to compare between the HBr and HCl in terms of acidity, I know HI is the most acidic, followed by the HBr, followed by the HCl. So HI would be reacting much faster here. But if I'm comparing right now between the HBr and HCl, HCl is not as reactive as the HBr, and anytime you're using an HCl, you typically use an Lewis acid, something like a zinc chloride, and that's also called an Lewis reagent. I'll talk about that in a minute, but let's see what really happens in case of these reactions. So if you have a secondary and a tertiary alcohol, they primarily go with the formation of this primarily due to SN1 mechanism, where if you recall, the SN1 mechanism could have both of the products. You could have the nucleophile back into the page, and you can also have the nucleophile coming out of the page. So at the end of the day, the product would have been the bromine here and the bromine here. So this is like the drawback here, that you actually getting two products here, and they have different stereochemistry. In addition to that, you can also get carbocation rearrangements anytime you're making the carbocation, and since this is an SN1 mechanism, you are going to be making a carbocation. So if I look up mechanistically what really happens, let's talk about that. So obviously I got this HBr here. I'm going to be protonating this alcohol using the HBr. And once I have protonated that, I'm going to have a new hydrogen there. Obviously, this is going to have a positive charge on it. And now, all of a sudden, this is a good leaving group, so I can go ahead and have this gone now. This bond breaks, and you release water, and you end up making this secondary carbocation. Now, if you're making a secondary carbocation, you always want to be on the lookout if you can actually do any rearrangements to make a more stable carbocation. But in this case, that's the most stable carbocation you can get. You can't really get any more stable, so you just leave it right there. And then you have two possibilities where, okay, I can have this bromide either doing the top attack, or I could have this bromide doing this backside attack, because this particular carbon is an sp2 at this time, and it's in a planar carbon, so it can actually have a 50-50 shot of doing the top attack and the bottom attack. So in either case, you either get to the bromine coming out of the page or bromine going back into the page. So this is how it's going to look like. It will end up making racemic mixtures. Now, if you're using an HCl, HCl being a weak acid, or relatively weaker acid, let's say, compared to the HBr, we're going to have to use zinc chloride as your Lewis acid here. So what that really does, your product's really not going to change in terms of what's going to be happening here. We're still going to be making two products. Let me just minimize those here. But instead of having bromines, and obviously I'm going to have chlorines there. And then I'm going to go ahead, in the first step, we're going to be using zinc chloride as your Lewis acid, and that's going to be doing the nucleophilic attack there, and we end up getting this right there, and then this oxygen is going to have a positive charge, this is going to have a negative charge. Now after that, you can have the loss of leaving group there, and once you have the loss of leaving group, so this kind of goes away, so you lose that particular guy there, and then you end up making this carbocation, and then you will have both the top attack and the bottom attack. Now remember, if you were using a primary alcohols, then you don't really make a carbocation, but in that case you do an SN2 mechanism. And if I give you a relative example here, like suppose this is my alcohol, and in the first step I'm going to be using zinc chloride there, and I'm going to be protonating this using the lone pair on the oxygen. And then once you had made this right there, I can't really make a carbocation because it's going to be making a weak carbocation, as it's going to be primary. So as a result, you can have this Cl minus coming in, and doing this back attack. And when this does the back attack, this is going to be going away. So this is more like an SN2 mechanism at that point. So if you have a primary alcohol, it will more or less go as an SN2 mechanism, and if you're in a secondary and tertiary alcohols, they like to go SN. If you have a primary alcohol, it likes to do SN2 mechanism, and if you have a secondary and a tertiary alcohol, it will like to do SN1 mechanism, where you have to make the carbocation, and you could have the possibilities of these carbocation rearrangements. Now, how do I really know the reaction has actually taken place? If you recall, the Lucas reagent is used in the labs as well to test whether you have a primary, secondary, and tertiary alcohol. This actually works only when you have water-soluble alcohols. And if I go ahead and change the color there, this alcohol right there is going to be water-soluble. So when you mix initially with HCl, ZnCl2, it's all going to be one solution. It's going to be a homogeneous solution. But as soon as you have made these products, they are actually not that polar, because alcohols are able to make hydrogen bonds, and that's how you can really dissolve the alcohols in the water. But all of a sudden you got these chlorines on it. So this is actually going to be not soluble in water, and as a result, they're going to make a separate layer. Now, how quickly you're going to be making another layer, based on the time you can tell whether you have a primary, secondary, or tertiary alcohol. So the timeline there, if you have a tertiary alcohol, you typically need less than a minute. And if you have a secondary alcohol, it takes about 1 to 5 minutes for those to make a separate layer, or you can say for those to react with the Lucas reagent. And if you have primary alcohol, it will take more than 5 minutes. So that's how you can tell if you have a primary, secondary, or tertiary alcohol based on this Lucas reagent. Now, suppose I have this question here where I got this secondary alkyl halide, a secondary alcohol. I'm reacting that with an HBr, and what's going to be the product? Now, you may think that your product is actually going to look something like this, where the bromine is going to be attached here. But it's actually no, because once you make the carbocation, it's going to have a carbocation rearrangement to make a more stable carbocation, and as a result, your bromine is going to be right here. So don't forget that you can have a carbocation rearrangement, and the carbocation in the beginning, once you lose this group after protonating and all that, let me just make this small a little bit, is gonna look like this. So that's, obviously protonating and losing the OH there. I'm not really going to draw the full mechanism, but I'm just showing that this is the carbocation you get here. And then since you have this as a secondary carbocation, I can have a carbocation rearrangement here. So this moves down here, and when you do this 1,2 methyl shift, your new carbocation would look like this. Going to have a positive charge there. So now from here you can have your bromide ion rather attacking that particular position. Now that particular position is really not chiral, so I don't really have to worry about this being into the page or out of the page, so you can just draw it one way. So remember, there's a couple of steps that I missed in the beginning. So I can have the lone pair on this oxygen attacking here, lone pair on the oxygen attacking the proton here, another way of saying protonating this, and that would make, let me just draw that right here. So that would make this OH2 here with a positive charge, and then the next step you can have this loss of leaving group, and you make this carbocation, and then you can have a carbocation rearrangement. Okay, now what if you want to use PBr3 SOCl2 or PCl3 or Pi3? So typically the Pi3 is not that stable, so you actually add the phosphorus and iodine together to first make the Pi3, like making a fresh Pi3, and then it reacts with it. This works mainly for the primaries and secondary alcohols, and it goes with SN2 mechanism. The tertiary alcohols are kind of crowded for these guys to react. For the most part, these guys will be reacting with an inversion of stereochemistry, so more or less they follow SN2 mechanism once you have installed a good leaving group on it. But then there are times when the SOCl2 has been seen reacting with these alcohols with retention in the stereochemistry. Now remember, if it's in a primary alcohol, you don't really have to worry about the stereochemistry. It's only when you have a secondary alcohol, and even if the secondary alcohol is actually chiral, has a chiral center. So if I'm using SPOs, so I'm not really going to draw the mechanism for every single one. So like PCl3, Pi3, and even like PBr3, they all going to have a very similar mechanism. So suppose if I use PBr3 and we said eventually it's going to do an SN2 mechanism, and your product would look like this. It's going to have the bromine now going back into the page here. Now, how does that really work? Let's talk about that. The mechanism, again, is going to be fairly straightforward. I can draw this PBr3 right there. I can use the lone pair on the oxygen to attack this phosphorus right there, and it's gonna knock out one of these bromine groups as in a bromide. And in that process, we're gonna be making, I'm gonna small that a little bit. We're gonna be making this guy right there. And then in the next step, remember there's a positive charge on that alcohol, on that oxygen. And in the next step, I can have this bromide that you just got from the PBr3 doing this backside attack. And at this point, it's kind of going in an SN2 type of reaction. And then obviously you're going to be making PBr2 LH as your side product, but you don't really have to worry too much about that part. Now, if I'm using PCl3 and Pi3, your mechanism is going to be exactly the same. When you're using PCl3, obviously you're installing chlorine instead of the bromine, and if you're using Pi3, then you're installing iodine instead of the other bromine and chlorine. But again, they all going to involve inversion of stereochemistry. Now, with SOCl2, if I'm using pyridine as my base here, so pyridine is a non-nucleophilic base, then it will do a complete inversion in stereochemistry. So I'm going to end up getting this guy right there where the chlorine is going to be going back into the page. So again, this is in a secondary alcohol, and it has a chiral center, so I don't have to worry about the stereochemistry. If this was not in a secondary, but rather in a primary, you didn't really have to worry about the stereochemistry. So mechanistically, again, it's going to be fairly straightforward. I got this SOCl2. So first, I'm going to be attacking this sulfur here from the lone pair of that oxygen. In the process of making that leaving group, the pi bond between the sulfur and oxygen breaks, and we're going to end up getting this intermediate. So I'm going to actually copy this down here and put it right here. Maybe make it a little bit smaller. So you already have a hydrogen there. And remember, I got this intermediate that has been made here. Now, when this pi bond reforms, in that process, it's gonna knock out this leaving group because you have a good leaving group in this particular case. So then, and don't forget there's a positive charge on that oxygen because it's making 3 bonds. And then you have, so I'm gonna erase this part right there. Gonna have a double bond here. Let me erase this part as well and remake it. Okay, so then in the next step, I typically am going to be using the pyridine. So I can just go ahead and draw out how the pyridine looks like here. I'm going to be using this lone pair on the pyridine to grab that proton and restore the electron density back on the oxygen. And this is how it's going to look like at that point. Oops, no positive charge, just two lone pairs. And then finally, we're going to have the chloride that you have actually knocked out in the beginning. In the first step, it's going to do this backside attack here, and this is going to leave right there. So what technically happened, this leaves right there to create the double bond there, and then the chloride leaves as well. So your side products are going to be the SO2, which is actually a gas. So this is a irreversible reaction, because once the SO2 is formed and it's in a gas, it leaves, and it's not really going to be reacting back to make this alcohol. So you can do this reaction with primary and the secondary alcohols, and in addition to that, you're also going to be making an pyridine salt here. And if I want to go ahead and draw that out, because remember you have protonated this pyridine to positive charge, and you're going to have the chloride just kind of hanging around there. But obviously your organic products is always going to be the most important when you're doing these organic reactions. So this isn't a complete inversion of configuration whenever you're using an SOCl2, so more or less follows similar to an SN2 mechanism, but you also have seen a retention in the configuration. So that usually happens anytime you're using an ether. So suppose if I'm doing this particular reaction, but instead of using a pyridine as my base and even as a solvent, we're just using an ether, so there's really not any base in this particular case. So in that case, this has observed to keep the stereochemistry as it is. So you're going to have chloride or chlorine coming out of the page, so you're going to have a retention in the stereochemistry. So it doesn't really do the SN1 mechanism, because SN1 mechanism actually do both racemic mixtures, but this more or less is called an SNI, which is technically um, nucleophilic substitution internal reaction. So there is usually an ion pair made that helps to retain the stereochemistry. So if I want to talk about the mechanism here, so first part is still going to be the same. So I'm just going to copy this down here, because you're still going to have this SOCl2, the oxygen here attacking this sulfur, the pi bond breaks here, and then you make this intermediate that I have drawn on the bottom here. And then in the next step, when it comes back, you knock out that chloride here, and then you end up making so let me just rearrange this part here. And then I don't really knock out this leaving group right away, because it's not really an SN1 type. You kind of make a carbocation, but it's in the form of an ion pair. So I can have this chloride coming back, grabbing this proton here, and this is restoring the electron density back in here. So this is how it looks like at this point. And now what happens is like in a nucleophilic substitution internal, where you actually do break this bond. And when you break this bond, this is going to have the positive charge. So you do make a carbocation here. So this gets the positive charge here, but then this is paired up with this negatively charged ion that you just have created. So it kind of stays close by. That's one of the reasonings you will find in the books. There are a couple of other reasonings, but this is the most prominent one. So then this kind of stays like in the ion pair form. And in the next step, what happens, this lone pair goes back to create SO2. And in that process, this bond between the sulfur and chlorine is going to break, and it's going to attack from the same side, and that's going to help it retaining the stereochemistry here. So this is how it's going to look like at the end of the day. And obviously your side products is still going to be an SO2 and HCl in this particular case here. So make sure you know when the SOCl2 can retain the configuration and when it can have an inversion. So if I want to really convert these alcohols to an alkyl halides, if you're using a primary alkyl halide, the best way to do it would be using something like PCl3, PBr3, or SOCl2, and then even phosphorus and iodine. Um, If I'm using tertiary alcohols, typically the HBr or HI or even HCl is recommended. And as far as the secondary goes, you can do either one of those. You can go with these, PCl3, PBr3, or even you can go with something like HBr or HI. The only issue when you're using secondary alcohols, it really depends on what type of stereochemistry you're looking at the end of the day. Whether you're looking for inversion of stereochemistry or you're looking for retention in the stereochemistry. So based on that, you can pick your reagent. So I got a couple of these examples here. So let's say I have in the middle, I got this secondary alcohol, and on the right side, I'm making an alkyl halide where this chlorine is actually coming out of the page. So there isn't a flip in the stereochemistry, you can say, where the OH was actually going back into the page, but now this chlorine is coming out of the page. So since there is an inversion, I can go ahead and use SOCl2 with pyridine, because that would do a clean SN2 mechanism. But I'm also trying to do where Cl retains the same stereochemistry type as that of an OH, so there isn't a retention here. So I want to go ahead and use SOCl2 in this case with the help of some sort of ether, where you can use, as an ether, you can use dioxane, you can use THF. As long as there is an ether, it will try to retain the stereochemistry. What about something like this? How would I really accomplish this particular one where the OH, secondary alcohol, is being converted into a nitrile group there? So there is a inversion in the stereochemistry. So what I can do is, in the first step, I can go ahead and use TsCl with pyridine. And in the second step, I can use a NaCN. Because if you recall, in the first step, when you use TsCl, I'm going to be making OH as a good leaving group, retaining the stereochemistry like this. And then in the next step, we can use this NaCN where this nitrile is going to be doing this backside attack. And when it does the backside attack, it's going to be inverting the stereochemistry there. So it's more like an SN2 mechanism at that point. So this is how you can accomplish that. What about if you try to retain the CN or the stereochemistry? So maybe in that case, the better way would be first you flip it and then you flip it again. So another way of saying do two inversions. So I can do that by either using suppose PCl3 and then, or even I can use SOCl2 with the pyridine. And in the second step, I can go ahead and use NaCN here. So then suppose in the first step, when I used this PCl3 or even SOCl2 with pyridine, we would have an inversion in the stereochemistry there where this chloride is going to be attached to that carbon going back into the page, and then eventually we're going to be using NaCN again So that's going to be doing an again an SN2. So two inversions will eventually end up being a retention at the end of the day. So this CN doing the backside attack will have this CN coming out of the page like I have shown in the products. So this is how you can convert these alcohols into alkyl halides. If you have any questions, feel free to leave any comments in the section below.